we're learning about exponential and logarithmic models, so story problems. So we're going to do more of that today. So we're going to have things like pH, the Richter scale, this thing called Newton's law of cooling. So we're going to do all this today. So the first one is a half-life problem. So we just did one of these on the board. So let's see if you can kind of do it along with me. So it says the half-life of strontium-90 is 28 years. So do you guys want to use the shortcut on this?
Yes.
Yeah, the half-life, or the rate, is equal to the natural log of 1/2 divided by the half-life, right? And you can get that if you did your A of t equals PE to the RT and put in like P and half P and solved it out. So our rate ends up being natural log of 1/2 divided by 28, which is a lovely decimal, which we're going to find on our calculator, and we're going to store. So I'm going to do stow alpha A. So I got negative 0.024755 something, and I stored that as alpha A. So I'm going to say that I have A circled. So it says, well, how long will it take for 50 milligrams to decay to a mass of 32? So that means that we want to find our T when our amount after T years is 32. So I want 32. Maybe I should write this equation down. A of T equals PE to the RT. You guys all know that. So 32 equals 50 E to the R, which we just stored as A, times T. And T is what we're trying to find. Does that make sense? Because I said, how long does it take for this to happen? So I take my 32 and I divide by 50. So I get 0.64 equals E to the A times T. And I take the natural log of both sides. So I do the natural log of 0.64, and then the natural log and E cancel, and my A of T goes to the front. So I have A times, not A of T, but A times T. So I'm going to take the natural log of 0.64, and I'm going to divide by that alpha A that I had in my calculator. And I get 18.028 years. We'll round to 3 decimal places in the end. Okay, easy? Easier than it was in Algebra 2?
Sure.
Yeah, that's the goal. So the second time you see it, you're like, oh, okay, I get this now. That's our goal. All right, so Newton's law of cooling is a very complicated formula, but it's used all of the time. The gory way that it's used, kind of disgusting way that it's used, is to calculate the time of death of a decaying body.
Awesome.
Yeah, kind of gross. No, I would give you this equation. So basically it's not a decaying, but a dead body. So if you arrive at the scene and the body is, I don't know, 60 degrees, right? And it's 30 degrees outside, you can figure out how long it took for that body to decay, or how long it took for the body to get that temperature. So it's kind of gross. All right, so Newton's law of cooling. So it depends on the temperature of our surroundings, right? So that would be kind of difficult if you found the person outside, because maybe it changed temperature throughout the night. It would be kind of hard. But if there's like, if you find someone in a house and their thermostat is set at 72 degrees and that body is now like 80 degrees, we can figure out how long it took that person, or how long that person's been dead. All right, so our formula's here, and like I said, I would give you this. And there's lots and lots of T's. I don't know why they couldn't use another variable for these, but we have T's all over the place. So we have capital T, which means temperature. We have little t, which means time. We have temperature subscript S, which means temperature of the surroundings. We have temperature sub-0, or sub-O, which means the initial temperature of the object, like when you get temperature of the object at time t. And then we have our temperature of, well, S, which is surroundings again. Okay, so let's see. So it says a roasted turkey is taken from an oven when its temperature has reached 185 degrees Fahrenheit and is placed on a table in a room where the temperature is 75 degrees Fahrenheit. If the temperature of the turkey is 150 degrees after half an hour, what is its temperature after 45 minutes? Okay. In this formula, we are always going to have T. Did I say this anywhere? T should be in hours. So T in hours. Yeah, T is in hours. I did say that. Okay. So we want to know that so we said that its temperature is 150 degrees Fahrenheit after half an hour. So this is T equals 1/2. And then how about 45 minutes? What would I do there for the time? What fraction of an hour? 3/4 of an hour, right. Okay, the room is the temperature of the surroundings, which is 75. So as we start putting things in, we have 75 plus, and when we took it out of the oven, it was 185. That's like the initial temperature of the object before it started cooling. Okay, so that's our T sub O. So I'm going to have 185 minus the temperature of the surroundings, which is 75, E to the R times T. So this is just like the half-life problems, this is a two-part question. So for the first part, we're using this. So my R I don't know, but I do know that in order for it to get down to 150, it took half an hour. So I put 150 over here. And what that does for us is it allows us to solve for R. So we're going to get the R all by itself. Okay, are we ready to do this? What do you think my first step is going to be? Yeah, subtract the 75 over. I get 75. I know that's confusing. You love when I do that. Okay, what about the 185 minus 75? That's going to be 110. E to the 1/2 R. I divide by 110. So I get 75 divided by 110 equals E to the 1/2 R. Now what? Natural log, so I do natural log of 75 divided by 110 equals 1/2 R. So I can find that. That's a decimal approximation we'll use. And then the last step is I get rid of my 1/2 by multiplying by 2.
Isn't it? Oh, wait, why did you put 185?
185 is the temperature of the turkey when it leaves the oven.
I put 180. Okay, sorry.
Because you're thinking 180 degrees like geometry. All right, so I get R equals negative 0.76598, something like that. And I'm going to store that, so I'll store again as alpha A or alpha B, whatever I want. Okay, second part of the problem. Well, what's its temperature after 45 minutes then? So we say, well, T of 45, or 3/4, I guess, the temperature after 3/4 of an hour. And most of these numbers are the same. So I still have my 75 plus my 185 minus 75. But now I know what my E is. So E is that A value I stored. And my time is no longer 1/2. Now what's my time? 3/4, right? Run out of room. Do you guys see that? A times 3/4. So I kind of do one thing at a time. So I multiplied my A by 3/4, and I'm going to do E raised to that answer on my calculator. I'm going to multiply by that 110, and I'm going to add 75. So my temperature after 3/4 of an hour, should it be above 150 degrees? Should it be below 150 degrees? What do we think? It's below, right? It's continuing to cool. And it continues to cool until it's now 136.929 degrees. So around 137 degrees Fahrenheit. So will it be like ice cold eventually? Will it be like 32 degrees eventually? No, why? What's it going to stop at? Yeah, 75, right? Why does it have to stop at 75? Because the room is 75 degrees. It's not going to automatically be like, oh, now I'm going to be in the refrigerator, right? It's 75 degrees in the room. That's the coldest that it can get. That's why it uses a logarithmic function. Okay, so there's like a limit to how cool it can get. All right, make sense? All right, so when will the turkey cool to 100 degrees Fahrenheit? So now this would be 100 degrees equals, and a lot of our numbers would be the same. So 75 plus 185 minus 75. Our rate of cooling is still the same, but now we're solving for T, right? How long? T. And so we do the same kind of thing. I take my 100, I subtract my 75 over, I divide by 110. I have my e to the a, t on the other side. I take the natural log of both sides, right? Natural log, natural log, natural log and e cancel. So I get negative 1.4816 equals a times t. So then I take my last answer and I divide by a. I get 1.934. What is that? Almost 2 hours, right? So, I mean, you could, what if I wanted to say like 1 hour and this many minutes? It's probably like 50 something minutes, right? But I could take that 0.934 part and I could multiply by 60 and it would be 56.04. So I could say 1 hour and 56 minutes, right? Does that make sense? But I think that's fine to leave it like that. All right. Do you like Newton's law of cooling? Does it make you want to go into forensic science and find out how long a person has been dead? I have no desire to do that. I don't know who likes to go into into houses and look at bodies that are dead. I don't know. It takes a special person. All right, so anyway, so pH scale, this is the easy one. So the pH scale equation is very easy. It's negative log of H plus. I think you could probably memorize that one. All right, so it says the hydrogen ion concentration of a sample of each substance is given. So this is our H plus. Okay, it's in the little brackets because it's an ion. Don't let that bother you. So it's going to be pH equals negative log of that number, 5.0 times 10 to the negative 3. And you can put that in your calculator in 2 different ways. So you can put it in just like negative log and then do 5 times 10 raised to the negative 3. That's fine. Or if for some reason you don't want to write times 10 raised to, there's a button that says EE, and you can do that as well. So we end up getting 2.3. We usually do 1 decimal point for pH. Easy? Yeah, so the next one, second enter, I'm going to adjust it to 3.2 times 10 to the negative 4. What did you guys get? Yep, 3.5. And the last one, negative log 5 times 10 to the negative 9. 8.3. Yeah. So if you remember with pH, if it's pH of 7, it's neutral, meaning it's like water. Water is the neutral substance. Anything that's more than that is what we would call a base. Anything that's less than that is an acid. So it makes sense for lemon juice that we would get an acidity of like 2.3. Yeah.
How much do you want us to round?
pH is usually just 1 decimal. So we can also go backwards. So we can say pH is equal to negative log of H plus. And if I had the pH given to me, I can solve. So if you want to write H plus as X, I don't care. Some people don't like the bracket and H plus thing. So in order to solve this equation, I need to first get the negative to the other side. And if I had that little subscript in there, you would know exactly what to do. So we do 10 raised to the negative 3.1. So I got X is equal to 7.943 something times 10 to the negative 4th. Did you guys get that? That's our H plus. So that's our answer. Okay. Feel pretty good with those two? We like pH problems? Should have done pH before Newton's law of cooling. Newton's law of cooling is a little intense. All right, and then Richter scale. So we have this formula. This would be another one I would give you. I think we did this exact problem in Algebra 2, now that I think about it. So it says the 1906 earthquake in San Francisco had a magnitude of 8.3 on the Richter scale. I think that's the one that led to like the San Francisco fire. At the same time, in Japan, an earthquake with magnitude of 4.9 caused only minor damage. How many times more intense was the San Francisco earthquake than the Japanese earthquake? Yeah, so we can find the energy released. So do you guys remember this is in ergs? That's the coolest math unit ever, ergs. I want to know who came up with that word. I don't know. But that's energy, so it's an ergs. And we're trying to solve for ergs for each one. So we're going to do two parts here. So our magnitude of the San Francisco one was 8.3. That is a massive earthquake. And we want to solve for the energy. So we're going to multiply the 3 over 2 over. So when we do 3 over 2 times 8.3, we get 12.45. All right. And then we're going to do 10 raised to both sides, right? So it's like 10 raised to that side. And I can write it as 10 raised to the 12.45 equals e over 10 to the 11.8. I like leaving it that way sometimes, so you can see on the next step we would just add the exponents. So I'm going to have 10 to the 12.48, or 45 times 10 to the 11.8 equals e. And I can just take these exponents and I can add them. So I have 10 to the 24.25, and we'll leave it like that. So you can find the scientific notation if you want to, but we'll just leave it like that. All right, so that was the San Francisco. And the Japanese earthquake was only a magnitude of 4.9. Only, that's still a pretty big one. Much bigger than like Indiana, which is like 2. Have you guys ever felt an earthquake in Indiana? I have a couple times. And then you're like, what just happened? It's not something that normally happens. All right, so we're going to multiply our 4.9 by 3 over 2. I'm going to do 10 raised to that. So it's 10 raised to the 7.35 equals e over 10 to the 11.8. I skipped a couple steps. So I add those exponents. So I have my 7.35 and my 11.8 that I'm going to add together. So I get E equals 10 to the 19.15. So these are the two different energies released. So it says, how many more times intense was it? Okay. So, I mean, when you talk about how many more times something is, let's say Simi has 5 Oreo cookies and I have 30 Oreo cookies. How many times more Oreo cookies do I have? 6 times. We know what that means. We know we're dividing. But for some reason, when we see things like numbers that look like this, we don't know what we're doing. So how many times more intense? You take your bigger number and you divide by the smaller number, right? You could subtract your exponents, so 24.25 minus 19.15. It ends up being 10 to the 5.1. And 10 to the 5.1 is a massive number. It is this number. So when I say how many times more powerful is it, it was 126,000 times more powerful than that other earthquake. So it doesn't look like a lot when you see like an 8.3 versus a 4.9. You're like, oh, you know, big earthquakes. But an 8.3 is a massive earthquake. Okay? All right, there is a shortcut to doing this too. I got to remember the formula, but it's, I mean, most of these steps are the same. I think you just take your, what is it, your 8.3 minus 4.9. I can't remember. There's like a shortcut to doing it. I'll have to look it up. All right, so the decibel scale, this is the last one. So it says hearing loss occurs after repeated exposure to more than 85 decibels. A certain rock concert has an intensity of 1.3 watts per meter squared. What is the loudness in decibels of the concert? Could it cause hearing loss? Okay, so B is always the decibel. I is the intensity. I sub O is the threshold of hearing. So it's what most people, the first thing that they can hear, the first level they can hear. My dad probably like 4 times that because he's deaf as can be. But what the normal human ear can hear. So we have B equals 10 log of I over, and that normal threshold of hearing is 10 to the negative 12. So we're just going to go ahead and plug that in. Yeah, so I don't know why they just don't put that in the formula, right? So it's going to be 10 times log of 1.3 over 10 to the negative 12.
Where's this 85 go?
Oh, we're just going to see if it's more than 85, yeah. So I would do my 1.3 divided by 10 to the negative 12. And then I do the log of that times 10. Yep, so you could do that all together. So we get 121.139 decibels. So could it cause hearing loss? Yeah. Have you guys ever been to a concert when you're right next to the speaker and you're like, oh, and then you leave and you kind of feel sick and a little dizzy? Like, why did I do that? Yeah. Now, if you're there all day, that would be an issue. If you're there for the length of a concert, probably not. All right, so a whisper has a loudness of 20 decibels. So that's going to be the 20 goes in for B. And then it says, well, what's its intensity? So we just solve it out. So I divide by 10, and I get 2 equals log of I over 10 to the negative 12. I put my little subscript in there, 10. So I do 10 to the 2 equals I over 10 to the negative 12, right? 10 to the 2 equals this part. And then I multiply it over. So I do 10 to the 2, and I multiply by 10 to the negative 12, and I get 10 to the negative, not 10 to the negative, yeah, 10 to the negative 10, right? What did I do here? 10 to the negative 10, right? I don't know what I did. Yeah, that's right. So it'd be like 1 times 10 to the negative 10 is what it would look like in scientific notation. So it's super tiny. It's like 0.0000. Yeah?
Do we need to memorize all of these?
No, you don't need to know that one. I'll give that one to you as well. The only one you would know is pH. Can you guys handle negative log of H+? I think you can handle that one. It's pretty easy. All right, so let's stop there.